Take it back.
Yeah. I think we're probably at forum. Now we're at Zoom. Cool. So today we are happy to have Linda coming from /Stanford. Linda was Lisa Randall's student at Harvard before going over to Berkeley. And then she wanted to test the waters at SLAC in Stanford because she loved the Bay Area so much. So today we're going to be doing a mental wellness check on thermal electroweak dark matter. So take it away.
Thank you. Thank you for having me here. We're happy to be here. Here to share this, our piece in this, like, I guess, very traditionally told story of indirect detection of electroweak with dark matter. I would love to talk to anyone afterwards and around the block.
So it's the challenge.
So we're gonna build up from the conclusions. I like doing that. But the way that I will start the framing of this whole concept is to point out that despite maybe the excitement from this general concept waning a little bit over the years, I still think that this core idea of a minimal electroweak WIMP is one of the most promising theories for the particle nature of dark matter. There's a lot of stuff that's theoretically compelling about it that is very well told, but perhaps has been kind of less emphasized over the years. The most immediate of which is that the electroweak sector is something just a natural place for physics. And a lot of these candidates that I'll be talking about do lend themselves as natural relics to, but do not necessarily have to require supersymmetric extensions of standard particles. There's also this empirically salient point of the so-called WIMP miracle that these candidates lend themselves to very straightforward cosmology. And for these minimal candidates that I will be talking about, that minimal cosmology picture then gives you extremely predictive phenomenology. And it identifies very specific experimental targets that are overwhelmingly experimentally unprobed so far. So the plan for this talk in a little bit more detail is to talk about Higgs in specific, kind of as like a benchmark scenario for how I will be talking about indirect detection as a whole. And then I'll do like a status report on the indirect detection for Higgs as a specific theory. And then at the end of the talk, I will widen enough to talk about higher SQL implications, nodes, contemplates, and so on. Okay. So I'm going to call this object a Higgsino, but you do not have to necessarily buy into the framing of what that should happen. Ultimately, for all of that to matter,
we've got a more.
Yeah.
No,
okay, so for all that you should care about for the purposes of this talk, all I'm talking about is a standard model plus a single SVP doublet. So the fellows at play are two neutral fermions, two neutral Wald degrees of freedom, and one charged fellow. At true level, they're all degenerate in mass. The charged fellow acquires at least radiative corrections from the neutral guys. And the neutral two fermions will very generically acquire some very small mass offset, either from the insertion of dimension 5 operators or the fractional mixing of heavier gauge nodes, depending on whether or not you prefer aesthetically to buy into the SUSY grid. But this is effectively a one-parameter model. There is one free parameter that is the overall mass scale. The couplings and what it couples to and how much it couples are fully set by the fact that I stated it's an SU2 doublet. if I combine that with the cosmology story, this idea that the thermal freeze out of annihilation gives you exactly the correct abundance of present day dark matter, this fixes a very specific mass scale as well. A thermal cosmology Higgsino that is 100% of present day dark matter needs to be 1.1, 1.08 if you want to be granted. But this now is a fully determined theory that we can search for. It identifies a candidate that is unfortunately out of reach for the colliders that we have today, but is a very interesting target for these future 10 TeV parton-centered class candidate colliders that have been quite in the public discussion. On the direct detection end, one of the major legs of the traditional WIMP detection program are these large underground liquid noble gas experiments where you would try to look for a TeV scale WIMP. The Higgsino would be a very luminous signal if this inelastic Z exchange were kinematically allowed. Unfortunately, because the dark matter is very cold, this channel is very easily shut off. If this mass difference is any larger than 200 keV on top of this TeV mass. So if you prefer to think about the MSSM framework, this is an equivalent statement to if the heavier gauginos are any lighter than like 10 to the 5, 10 to the 6 TeV on top of this 1 TeV Higgsino, then this channel is fully kinematically forbidden. And the next leading order signal, the elastic scattering, is unfortunately deep below the so-called neutrino fog, the threshold beyond which detection becomes needed. I would like to highlight some kind of recent local work from folks at Stanford that aim to kind of push the luminosity of this inelastic Z exchange signal to slightly higher mass gaps. But it does involve surrounding existing detectors with a large amount of heavy elements, 20 meters squared of lead or uranium. So it's an interesting possibility, but costly and quite futuristic. So that's kind of where we stand in the search scenario for the Higgsino. The last leg of the typical WIMP search program is indirect detection. I will be spending the rest of the talk on that. So that is a plot of roughly what the state of the art was when we came to this problem a couple of years ago. The constraints at that time were about an order of magnitude off from proving the Higgsino prediction. But they were based on data sets. The analyses were based on data sets collected about a decade ago. 4 experiments, both of which Fermi and Hess, which I'll talk about, both are still running today. And so even on that basic level, it was worth going and taking another look at the problem. There's also the aspect where the next generation of indirect detection experiments that we'll talk about for the energy range are coming online much sooner than we can get the next generation collider. At least early 2030s, if not soon. So it is, I think, quite likely that if Higgsino dark matter is our nature, that the first place we will see a hint of detection is in this indirect signal. This, of course, does not mean that we shouldn't build these other experiments. They can teach us things that indirect detection never can. But we're going to pursue first light first, and this talk will be about the indirect detection. So for any students in the audience who don't spend their time thinking about these things, just for context, indirect detection is a search for standard model particles that are produced by typically dark matter number changing interactions. Astrophysically, where there is a large accumulation of dark matter, and then the standard model particles propagate to us, where we detect them with detectors on and around Earth. The largest signal that you could target for this candidate would be gamma rays from the annihilation signal in the center of the galaxy. So that's the thing that we will be looking for the rest of it. The signal that you would expect from this sort of process can be pretty neatly factorized into these spatial and spectral coordinates of what the signal looks like spatially on the sky and what it looks like in energy space, which actually kind of cutely factorizes the problem into astrophysics and particle physics. So the spectral behavior first. The shape of the Higgsino annihilation flux in energy space is a thing that is complicated in detail to compute, and I will talk about this more at the end of this talk. But it is intuitively easy to understand. On the lower energy end, there is a soft continuum coming from the cascade and decay of dark matter directly annihilating into unstable electroweak gateways. And on the higher energy end, at exactly the there is this sharp spectral feature that comes from, among other things, the loop level annihilation of dark matter to photons, because the dark matter is very, very cold. The photons produced live exactly at the I have this cheeky cartoon that I like to use. If you want to look for the great white whale of new physics underneath the sea of background photons, you can look for either of these features in isolation. This large set of continuum photons that do make up the vast majority of the photon counts, but in shape is a little bit more degenerate with the background, or you can look at these smoking gun signals that are much more difficult to explain astrophysically, but in terms of raw photon count, do take up a much smaller bit of the signal. I wanted to share that I spent most of January at the KATP, and I went whale watching for the first time in my life. And I was extremely shocked to find that this was kind of how it worked in real life. Like, I went whale watching and I saw these large distortions in the water that propelled our captain to move the boat closer. And then we got to see a couple of these spout things show up that indicated that the whales were definitely there. And then the whale fully came above the water and ruined my for a little bit. Made the experience more fun. Okay. So the spectral behavior is something that's actually very well predicted. In sharp contrast to that is the astrophysical bit of the problem, which is how much signal you expect and how you expect it to be distributed on spec. And the sticking point is that we simply don't know the distribution of dark matter in a galaxy. We don't know how to measure it, and we don't know how to predict it. The thing to do in this space typically is to fall back on n-body simulations based on cold dark matter in physics. And these do give pretty universal behavior. This is the perhaps well-known NFW and NASTA prescriptions that you commonly see in indirect detection literature. On the other hand, like baryons, generally speaking, exist convincingly, and in specific, do dominate the gravitational potential in the inner parts of the galaxy. They dominate that potential even up to like where we are, 8-ish kilometers. And so neglecting them in the modeling is a known piece of is a known flaw in these sorts of simulations. In an attempt to get a slightly better ansatz, we have turned to these hydro-intensive simulations. So this one is from the FIRE collaboration, feedback in realistic environments, and they do these considerably more expensive, but hopefully slightly more realistic simulations that incorporate a lot of baryonic feedback into the process. these are the J factor maps of galaxies with and without baryonic input, and just even on a qualitative level, they're visually.
So does this now solve the core cusp problem, right, with this baryon feedback?
So it is a little unclear. So it's definitely true that baryons give you more chord profiles. But the amount of feedback is something that is dialed, and it's not very clear that these simulations all agree on what this shape should be.
So there's still room for self-interacting data.
There is still room.
Of course, in your scenario, you won't have that.
I will not.
Yeah, but
yes.
but
yes.
so you would rely on the baryons. So
Correct. The Corpus problem is also not, like I'm looking at the Milky Way. The Corpus problem is it's more of a noticed problem for like the North galaxies, for instance. Yes, I was thinking that so this fire collaboration gives us a suite of 12 Milky Way like hydro simulations, each of which gives us a different dark matter profile and corresponding J factor. The J factor is like the integral along the line of sight of the density square. So it's a direct measure of how much annihilation signal you expect to see. Let's see. There's a lot to say about these things. I should maybe highlight that 6 of these, the ones are highlighted here, were evolved in pairs to emulate the dynamics of Milky Way and Andromeda. Have that additional layer of realism and corresponding experiments associated with it, like Juliet with Romeo. But each of these, so this gives us 12 possibilities for what our Milky Way could look like. For context, because I will refer to them by name later, these simulations are bracketed by the galaxy named Romulus and the one named Thelma, Romulus at the top and Thelma at the bottom. So I'll be referring to them by name to talk about, I guess, the most aggressive and most conservative of these fire hypotheses. So there's a lot to say about these, but I'm going to say the 2 most obvious things, which is one, shape-wise, they are extremely different from these cold dark matter profiles. The cold dark matter profiles are noticeably cuspier, and the hydro profiles are much more chord. They're not necessarily less abundant than lines. The second obvious point is that these 12 galaxies that not only come from exactly the same physics, give you a gigantic variation in how much dark matter you expect. It's like a factor of 30 difference in this plot, which means a factor of 30 of potential signal you could expect on the sky. And it's very difficult to tell which of these scenarios would more or less likely to expect.
Wait, you said the J factor is already integrated along the line of sight. So what is this R? Is that
So
just
this is a degree from the center of the galaxy.
oh
Yeah, so I'm looking at the center of the galaxy, and I can look like 1 degree offset from it, or 2 degrees offset.
I see. Okay. How good angular resolution do these like gamma ray detectors have?
The spatial resolution of like of some of the spatial resolution of something like Hess is at the point of 2 degrees. It's it's got like a 2 degrees. It's pretty good. Like the limiting factor for this is actually the resolution of the simulations. You need to put in enough particles to resolve the J factors that we've inherited.
Okay.
But instrumentation wise.
For the paired simulations, is there some general qualitative difference than the single ones?
anything in here, you know, in the profiles.
So like, oh, like, are they, I guess what sort of quality?
Like say for the, for the paired ones, is the dark matter more between, you know, is it more spread out than the single ones, you know?
I don't think so. I don't think so. I think each of these have their individual roles. Certainly at the level of like this, this is like intercoupled degrees. They're not, yeah, they're not meaningfully together in the end.
Okay.
It's a little like it adding in these pairs does give you like just a large spread in how much dark matter you would take you would expect, right? I don't know what like how to model.
I mean, there's, yeah, it makes you think there's probably a lot of complications, like maybe two galaxies can bring in more dwarf galaxies that are bringing in more dark. You know, I don't know, there could be a lot of complications.
It's true. There's a lot of different things that, and one of the things maybe to point out is that all of these galaxies use this collaboration feedback. And there are other types of, there are other, you know, there are other groups that do hybrid simulation, and they in general tend to not quite agree. So later in the talk, we'll bring out a different hybrid simulation. It will look different.
Wasn't there, wasn't there a big attempt to sort of synchronize all hydro simulations at one point? Or to, yeah,
There's been a couple of attempts to I think, yeah. That was the couple simulations, like couple simulation suites that do have the JMAP. If you need to look for kind of this simulation for the thing to be enough resolution for the other couple degrees, which makes it. So yeah, for this you need to consolidate, and you can bracket the kind of the conclusion, which effectively is what we're going to do later on. I'll bring in another simulation, and that one plus fire those gives you like for the whole region. So I think maybe the big takeaway is like this is a giant point of uncertainty that probably towards everything else in the problem. And if there's one thing that we really narrowly follow it. But I want an answer to that. It's a large.
In each of those simulations, were they all using the same physics, just like changing the initial conditions?
Yeah.
But presumably still trying to match onto our like current observed distribution of stars or something like that.
Yeah, they try to match the abundance and that with the about stars. But and then they do a couple of other things to try to match the like for the nuclear like for galaxies with like disks that look approximately correct. But they still have like thicker and thinner disks among these bulbs. Some of them have better or worse LMC counterparts. For these simulations, you can like throw in like an LMC of the correct type. You have to select for ones that kind of look like they have the correct size of thing coming in at the correct time. Some of them match a little bit more. Experimental pairs. The data sets that we'll be considering. The ones that exist. There's clearly Fermi and Tess. So Fermi is probably a lot more well known. Part of it's satellite telescope looking for DOD gamma rays. In space, it's been scanning the sky for 15 years, and it sees the galactic center over one. Here is a continuous galactic center. On the other hand, is maybe a class telescope that is slightly less optimized. So it's one of these imaging Cherenkov telescope arrays. They look for the Cherenkov flashes that come from these ultra high energy gamma rays striking down. So they target much higher energies, the TV or above. But they're on the ground and they look for these Cherenkov flashes in the atmosphere. So they have like the sky as a canvas and have effective area in units, kilometers per meters. The trade-off is that they're pointing telescopes on Earth, so they see like 2 degrees of the sky at once, and they require like pristine nighttime or early vision. And so over the same amount of runtime, I think has started in 4, Fermi started in 8, has collected maybe 800 hours of data. So that's a trick. One of the maybe most important next generation players to look out for is called CPA. It is in effect just like a bigger, better, larger effective area, better energy resolution, like it's got a south and a north component. The south one goes to Chile. It's starting to be constructed at the foundation level, but it is the machine that you would ideally want to use for galactic. Southern galactic center directly overhead. Sometime in the early 2030s. CTA North is, I think, slightly underappreciated for dark matter physics. It's going to be in the Canary Islands route thing. And it does see the galactic center, although at a much lower horizon angle than the south component. And that will give it worse energy resolution. But the salient point is that most of it actually already exists, and the full array that is relevant for dark matter physics is expected to be online and taking data by next. So I'll talk about what we can do with both aspects of the theory. Good. Okay. So here I'm going to spend the next 15-ish minutes giving a status report on indirect detection of Higgs in specific. It'll be kind of condensed. But I'm happy to talk about details and the questions, and I'll present this in like dramatic trilogy. That's the one. So a couple of years ago, 2022, we looked for the continuum part of the signal, which is the thing that Fermi has most sensitivity to, with Fermi, with the open and publicly available Fermi. The sky that Fermi sees, especially at the energies, is overwhelmingly dominated by the diffuse emission of flashes, gas, things like inverse Compton. So that, if you want to see the hierarchy of the signal and that diffuse annihilation, this is the order of magnitude. So I could and have spent entire talks talking about this paper. For brevity, I'm just going to say, did this analysis? If there are questions, I'm more than happy to. But the upshot of this analysis is that we found this kind of mild 2 sigma statistical preference in roughly speed. The statement of this statistical preference is mildly profile dependent because it depends on how much the way the different spatial regions are. But the interpretation of that translation from the preference for an excess flux to a best fit cross section is most aggressive one, we can plot a cross-section versus mass. Plot. And we find that the cross-section activity mass is roughly consistent with the Higgs theory. Yeah, so this is and again, like a pretty mild preference, and you should take it with at least as many totals as you see on the page. But we found it not motivating because this is, I think, a priori very compelling theory. And if this is in our nature, this is kind of the first thing that we do. So I think we took this define follow-up. And the things that you would want to follow up is at these TV telescopes that have the sensitivity and resolution to hopefully resolve this motion by line feature. So the thing that I should mention here is that for these ground-based Shannon telescopes, there is a much larger additional fact, which is that there is large flux of mostly proton, mostly extragalactic or cosmic rays that are constantly striking the atmosphere and also radiating to light. These flashes look different from gamma ray flashes, so experimentalists are actually pretty efficiently able to reject this signal. But even like a 99% rejection rate still gives you a residual background that dominates over everything else you see. So in this case, the thing that is eating up all the counts are this 1% of misidentified, mostly proton. And then beyond that, there's snack point, and below that, there's Higgs we expect to see. The saving grace is that both of these signals are much smoother and we're looking for a lot. So even though it's several orders of magnitude below, we're going to hope to be able to do that. As for how publicly available data, so the thing that we ended up looking at was this paper that came out a couple of years ago, right around when we published our Fermi study, that uses basically the data set that we would have liked to use for our analysis. This is all of the galactic center data that has collected to date. They search for dark matter annihilation, albeit they search for this continuum WW signal instead of the line signal. We would like to look for. But no matter, like we can get a sense of what their spot sensitivity is based on their analysis. And this actually really excited us because the flux sensitivity that was implied by their constraints really implied the ability to either confirm or reject this weak signal that we found in the Fermi data at a really high significance. With data that someone has already collected on disk. There are some details involved. The analysis strategy needs to be heavily modified. But this paper implied that they had the data to give us the answer. Unfortunately, after looking at the results for a longer period of time, we came to the conclusion that the results were mischaracterized by like quite a large factor close to the fact. So I'm gonna acknowledge that this is kind of like an inherently antagonistic statement. I'm gonna spend 2 minutes kind of justifying where we come from. But I do want to emphasize that we do not have access to their data. Everything that we have to say comes inferred from their published results. So the thing that we think is ultimately true is that even though they don't publish like full details about their observation strategy, the same thing has to connect the flux they see from the sky to the counts that they see in the detection, whether the flux comes from dark matter or from this cosmic ray background or from the galactic frequency. And they use this on-off strategy, which is approximately speaking, they take regions of their data that are closer and further away from from the galactic center, and they look at the difference. Um, because the cosmic ray background is largely extragalactic, it is almost entirely isotropic. Right? So the difference between the on and off regions is dominated by the diffuse emission and any potential dark matter. Whereas like the total amount of counts in both the on and off region give us a sense of how much the cosmic ray, how much of the cosmic ray background they can. But so they don't again publish a lot of details about their observation strategy. But we were able to use bits of small amounts of publicly released data to reconstruct what we think their exposure looks like. This is not a perfect endeavor, but I think I just wanted to demonstrate that it's not the same. Like the left is their actual published exposure map, and the right is our best reconstruction of it. Again, it's clearly not perfect, but it's not terribly insane. The thing that convinced us that we have their forward model down to a reasonable amount of accuracy is that we were able to pretty perfectly reproduce their dark matter analysis. We know what flux this cross section needs to find, and we were able to reproduce their constraints based on what they think their sensitivity is. So that means I think we have the thing that connects flux on sky to time limit. So this allows us to do things like estimate what sort of cosmic ray rejection they must be working. And to get this amount of flux sensitivity, they needed to have rejection efficiency that was about an order of magnitude stronger than what was stated to be doable by the collaboration and other people who do telemetry. The thing that really convinced us as non-experts in terraform telescope arrays is that fermion and Hess have a non-trivial energy overlap, and they both look at the galactic center. So within that region of overlap, they need to be seeing the same photons in the same energy range in the same time. And to good approximation, the photons are seeing. So if I just pipe the flux, the galactic diffuse flux that Fermi sees through this forward model, I should get, to good approximation, the amount of difference they see in this on and off region. And I get something that is spectrally consistent with their on-off residuals, but a factor of 8 different. And since the Fermi flux is actually very well validated by other experiments, lower energies, and is also publicly available, we tend to trust it a little bit more. And the only way that we understand how to reconcile these things is that the flux sensitivity of Hess is actually after 8 worse than a state, which means that unfortunately the dark matter results are like an order of magnitude worse. So this is like a disappointing conclusion to come to. For us, it at least means that we don't currently, with the data that we have the ability to say anything about TB annihilation.
So what does Hess say?
This is a very good question. The short answer.
I assume they've seen your paper and read it all.
Yeah, so we've been in, well, we were in correspondence with Hess for a good amount of this paper. Like there were people from the collaboration that were co-authors with us at the beginning. But once we identified this issue, I mean, like their collaboration with the tools. So these people exited from our paper and kind of cut off communications with us. It is quite possible that the response is being prepared and they're not allowed to talk to us about it. But from the outside, thing that was
But the paper's in preparation, saying they're gonna respond.
maybe, like, I think, I don't know because they haven't told
They're
me
not
that.
allowed to talk.
But, I think like if there was a paper, a response paper in preparation, they would not be allowed to. So. that's all.
So I see, I see you're usually using S sort of limits. So there's also magic and a couple others, but I'm assuming S is the most sensitive, and that's why you're usually doing that one.
Yeah, so, so there is magic data and that is like one of the, so magic has, I think, comparable sensitivity to, which, uses a fraction of, which makes up really like a fraction of the galactic center that has been able to collect. So we did take a look. They just had, yeah, they had less sensitivity than this paper stated. It was just about enough to get to the data. So I think I'm inclined to think that at this point, magic probably be sensitivity in this space. Totally quite enough.
You said that you used Fermi for the like the broad part of the spectrum and Hess for the line, right?
Yeah.
Is that true? Like, can Fermi see the line as well? Why not use Fermi for that?
Wait, what's that? It's
Oh.
the problem is that it gets killed by, hasn't worked with the clock, it's where it's temporary. So it does see photons up until a couple of TeV, but the photons are not enough. Because of the power. Anyway, like if those, you have to be expert in the audience on this with opinions that they're allowed to share. I would genuinely love to be wrong about this. I'd love to have more accurate data. So, antagonism politics. The problem, yeah, so we ended up with kind of a disappointing conclusion. But like all trilogies that end with their lowest bit and the end of their second installment, the third installment is legally obligated to deliver a message to it. So we're going to look into the future for what we can do with CTA. Okay. So once again, there's north and south. South is the thing that you would want to use for the galactic filter, all of things equal. North is able to achieve approximately the same amount of effective area at a TeV as south, albeit doing worse in the drawing to field of view and energy resolution. And it's coming online next year. And as little goblin particle theorists, we want data as soon as we can get our hands on. And it will, and CTA as a population expressed a lot of interest in the data. Okay, so as promised, we're bringing in some extra simulations at this point and making the giant dispersion problem a little bit worse for ourselves. So here is the Auriga class of simulations. It's one of the ones considered in the Lena paper that I mentioned earlier. She was the one that pointed us to simulations. They're just other hydro-intensive filter-wave-like simulations. And the combination of Auriga and fire just makes this possible range of dark matter distributions much larger. But it is worth noting that Auriga systematically predicts more dark matter in the center of the galaxy than fire does. It's difficult to pin down for sure why, but it is known that fire has, like an uncharacteristically strong and aggressive feedback. It tries to compensate essentially for not having black hole feedback in the center of the galaxy by making their star formation feedback extremely bursty. And it is possible that that prescription expels more material from the center of the galaxy than is strictly necessary. This doesn't necessarily imply that Omega simulations are translated, but reality means that they don't necessarily prove. If we take all of these equal possibilities, that does strictly make things better for the dark matter. For instance, Romulus, which we originally took as an optimistic benchmark, is now kind of in the middle. So, you can quickly ask the question of, given CTA North turning on in 2026 and CTA South turning on, let's say, optimistically in 2031, how much observing time do we need on the x-axis to accumulate enough statistical evidence for X sigma discovery y-axis of Higgsino dark matter, assuming again 100% that Higgsino dark matter is answering on. And that is a question that strongly depends on what dark matter is. In the median profiles given by the Omega simulation, we can actually get 5 sigma discoveries extremely early. About a year into CTA North turning on. And for these kind of more middle of the path INASCO NFW full dark matter profiles, we can expect perhaps 5 sigma evidence within 5 or 6 years of CTA South turn. And even in these like slightly more poor medium fire scenarios, we're looking at something approaching 2 to 3 sigma evidence within the proposed runtime of case out, which I think for a worst case scenario is much better than expected. So I think there is reason to be excited, and there's reason to be excited much sooner than I personally expected. If I look again at the range of J factors that the simulations have predicted, every one that's highlighted in blue, you can potentially expect 3 sigma before the end of the decade. Again, much more optimistic than I would have naively expected. So I think it's exciting. This is motivation above all else. Be excited for CTA North in specific. In general, CTA South will dominate the sensitivity once it turns on. Take a couple years back. Okay, so I think there's still reason to be excited despite how the current data is shaping up. And I have until 100.
35 or something, I mean, or
Okay.
more, yeah. Can I ask a random question
Yeah.
though? So, yeah, I mean, so if we start seeing something that's consistent with like 1.1 TV, then we get like pretty excited. Like, hey, this is consistent with 1.1 TV, and we see this bump like nearby. So like in the flip scenario where like, okay, we're like now starting to probe these larger J factors and stuff. Like, is there some like relatively, like, I know we're saying like, okay, we're gonna take all these different simulated J factors as like maybe equally likely. Is there some point where like now we're probing J factors so small that like reasonably we think like we're starting to rule things out, or like is that a difficult thing to answer?
It is. I think it's a difficult thing to answer rigorously because there's not a great way to like establish sigmas in these very finite selection of hydrosims, but I'm going to talk about some other SU2 representations, like for instance the WINO, and the WINO is a good example of I think these will out by indirect detection for reasonable trade. And, I will give you an example of that. But it is hard to do at a very good. So. Okay, higher real representations of SU2. Yeah, so for simplicity, these are the real odd dimensional representations of SU2. The flow is at play, so now there's one single neutral degree of freedom. It's always the lightest, it's always the dark matter, and then a tower of increasingly charged things that are increasingly offset by increasingly large radiative correction. Within this tower, adjacent rungs can talk via W exchange, and charged particles can talk to themselves via again. The WINO is a triplet, so it's got the dark matter and one singularly charged thing. The quintuplet has one has a single and the doubly charged thing. So once again, this is effectively a one-parameter model. There's one overall mass scale, and that's the only thing you can change. And assuming this miracle scenario that freeze out gives you 100% of the dark matter, fixes that mass, and gives you exactly what mass predictions should be for each of these possibilities. There's like a finite amount that you can where you can go before you just truly hit perturbative unitaries. So these are like generously the ones that you can conceivably fit in. The masses get pretty high.
So the Landau pole, where's the Landau pole? It's pretty close to the TeV scale, but n equals 13. So.
Yeah, exactly. So I think n equals 13 is really kind of saturated.
It's the new physics already at the TeV scale. Besides this.
Yes, it is. Yeah, the WINO, maybe the quintuplet are plausible targets for future high energy colliders. Although for the quintuplet, I think we're talking like 30 TeV neuron colliders, so a little bit further than we personally see. But the WINO certainly is one of those. Is another key target for these candidates. On these, in the end of direct detection, all of these candidates kind of sit right around near where the neutrino fog is. So it's kind of getting difficult to look for all of these things. There's no inelastic exchange, do loop level elastic exchange here. The Higgsino lives, again, sadly, all the way down here. And so these are valid but difficult targets for these experiments. There's been some relatively recent work that shows that these are accessible targets, but for some very aggressive future really up the amount of xenon in your reserves. That says 50 times here.
Wait, naive question, why is the Higgsino so much weaker interaction than the WINO?
I think it's a they have, so the WINO has the Higgsino has like WMZ exchange. And I think it just happens to cancel.
But it's also a loop level process.
It's also
Why is it just a point, not a strip?
so the WINO, so what I will
This in the limit that all the other super partners are infinitely heavy, or?
good, so all of these are kind of in the limit that all the super partners, if applicable, are much heavier, but the thermal mass determination has a much larger error bar for these higher multiples.
No, I mean, just the Higgsino, why is it just, well, I don't know about the other ones, but
yeah, so
Higgsino should be a whole line that goes up. I mean, there are models of Higsinos which are already excluded by experiment.
oh yeah, sorry, this is yeah, so these are like nearly pure Higsinos and nearly pure WINOs. So like
Well, it could still be nearly pure, but at some level it has to depend.
Not nearly pure. Here, she assumed pure electric double.
Yeah, so like,
So infinite,
Yeah,
infinite
infinite,
masses for everything
for
else.
everyone else.
approximately, like enough to offset the two neutral fellows by a little bit, but not enough to do anything else. So like, I think at least like, I think 1 to 2 orders of magnitude. Because, heavy rotations.
In the Higgs, you have one free parameter, which is the mass splitting, and in these other ones, there's no free parameter.
So
Well,
sure, like in our prescription, yes. If you like, yeah, these are things that you can model both around too, but we have assumed. The things that separate these charged particles are just radiated.
So here you have already played the game of splitting the two neutral components in Xeno so that I avoid the direct detection.
That is correct. Yeah, like otherwise,
Well,
the
there's a
truly
limit,
pure
right?
is full infinite mass as a fact. But if you,
You're choosing.
again, if the GGOs
You're thinking.
are less than like 10⁶ TeV,
Offset everything.
yeah, so the hierarchy is
Yeah,
less.
you are generating some minimal.
Yeah,
splitting.
then the splitting will be enough.
Anyway, Chan.
So in this regard, you already used the other component just to avoid
Correct,
the direct
Like
detection.
it is
So
not,
it's
that's
not
why,
pure.
that's why
pure
I keep
double
saying
laser.
nearly pure.
Right.
It's like the GGOs need to be like, like heavier, but not like infinite.
So split the mass gap enough to push it into the fog. That's what
Pretty
you
much, like,
Yeah, and you put it as
so
a point
basically,
here.
if you shut off the inelastic scattering bit, it's immediately deep. The GGOs need to be, for the Higgs less than 10⁶, not infinitely higher. If it's 10⁵, the only thing it'll do is push the Higgs out of the magnets. Good. So reasonable targets, but kind of far in our future. But they do all make potential targets for indirect. We're talking about, you can once again look for the line at increasingly higher energies, or you can look for the continuum. The thing that becomes inevitably necessary to talk about is that these predictions become more and more involved. The thing that is necessary to actually accurately predict the magnitude and shape of the annihilation spectra for these templates, you need to account for summerfold enhancement and downstate formation, and to accurately predict the magnitude of the line, you additionally need to take into account all of these large logarithmic corrections from soft collinear fluids, finite energy resolution, and pseudocog corrections. And so I think this is the subject of an imminent paper by Nick Rod and Tracy Slatter and company. I will not be touching that. But I can compute the first 2 parts of this process and isolate the continuums. Once you can get the prediction, these are valid fodder for any of the experiments that I talked about. For us, once again, Fermi is the data we have. The continuum is the signal that I personally know how to compute. So we're going to search for A with B. Even for a 10 TeV, 100 TeV signal, you will produce soft photons that are within the Fermi energy. And these large, because of these effects that I'll be talking about, these increasingly heavier candidates all have increasingly larger present day annihilation costs, making this a viable strategy. So in maybe 2 seconds, detail. In two sentences worth of detail, Sommerfeld enhancement is the effect where, because these candidates are so heavy, the exchange of electric gauge bosons becomes effectively long range. And so the attractive potential generated by two incoming dark matter particles strongly enhances the probability that they annihilate. So to account for this, you solve, okay, to account for this, you solve a complicated Schrödinger equation, and you acquire, you see this behavior that has these like sharp resonant features. This is where effectively you form zero energy bound states in your electric potential. The Wino is actually one of the really good examples where where this like effect is extremely important and that is fairly well advertised. The thermal mass of the Wino happens to sit pretty close to one of these Sommerfeld resonances. So that means that the present day annihilation, the annihilation that you would expect at velocities of 10 to the minus 3, are significantly enhanced over the thermal velocities, the velocities that set the dark matter abundance, peak of our process. And that means the present day annihilation, the stuff that you would expect at the center of our galaxy, for a thermal unit, the annihilation cross section is enhanced about 2 orders of magnitude above what the Pico-Barn freeze out cross section is. And this allows us to place extremely strong constraints on annihilation of the Wien. So this is one of the cases where, unless the dark matter profile is much, much lower than any simulation has to do, this requires, I think, a 3 to 10 kiloparsec core to get the Wino to be like a viable candidate given current data. And nothing that simulations have done have seen anything close to that. So again, it's hard to make a rigorous statistical statement. But that is the sense in which a thermal Wino making 100% dark is kind of a disfavored scenario. You do this for the other outlets. Again, the higher up you go, the larger these numbers tend to become. But also the larger the error bars in the thermal mass determination is. Even by the time you get to the quintuplet, you are traversing several of these resonant peaks, many orders of magnitude within the possible thermal mass range. But really, but we can ask the question for these cross section predictions. In this mass or an annihilation space, what general region of predictions that do they contain? Do they take up? And what general space can Fermi rule out for these masses annihilating to W? So this is where the constraint lies, assuming the thermal profile, which is our most conservative of our guesses. And even here, you can already see that we're saying a good amount about these predictions for tens to 100 TeV dark matter. And we're able to do this because of these strong enhancements. Add in bound state formation, which we don't have time to talk about, but it's important for higher and higher endlets, and moves all these predictions up a good amount, albeit lengthening the uncertainty of these cross sections, depending on where on this resonance you're sitting. So this is really preliminary results that are rapidly updating. There are more analysis tricks that we can play, so hopefully this will get a little bit better. But even at this stage, I think it's pretty clear that there's still some interesting stuff to say about, minimal dark matter, even with the data that we already have. It's really hard to rigorously rule these out, but at least we can say that this, in conjunction with all of the hydrosims that we've been able to dredge up, are not compatible descriptions for. Good. So I think that's all of the story we have to share. Hope you'll agree that there's still interesting stuff to do, and stay tuned about what the results. Thank you.
Last slide, when you show the projection for the higher multiplets, which part of the spectrum you are using to make this projection?
Just the WW. So like this is just with
Still
Fermi.
the low tails.
Yeah, exactly. So Fermi has no sensitivity for the line
Right.
at 100 TeV or something.
Yeah, but I would call the line being the discovery mode, right?
Yeah,
The
exactly.
tail is access, you know, up to your modeling of all sorts of
Yeah,
diffuse
yeah.
background cosmic rays.
Exactly. So with this, all we're hoping to do is place constraints and not discovery. We do the thing where we're very, like, we assume the aggressive potentials for discovery, conservative ones.
Also a comment when you say colliders, colliders don't probe those higher multiples, that's not right. Okay, although direct searches for them, of course, requires higher energy, but they actually have induced large electroweak corrections. So even just a precision drill EM measurement will give you access to these higher multiples. There are some studies on those higher multiples from electric precision at high supermass energy.
That makes a lot of sense. I hadn't thought about that. And I'm certain you're right about it.
Oh, so the question, when you're going back to the Hess results, so they released this analysis looking for the sort of broad continuum spectrum, right? And then you guys wanted to look for the bump. And then, yeah, accounting for the factor of 8, then it's like, okay, probably can't. But is there any slight improvement if you tried to do some like, yeah, more global thing with like both of these simultaneously?
Like joint analysis.
Yeah.
Um,
Like presumably not some huge improvement, but I don't,
I think the improvement is probably the thing is, like, for me, is really not the ideal data set you want to look for these things, because you will fundamentally be choked by the inability to measure the shape of the background at the precision necessary to suss out this one. So if you have basically any line sensitivity at all, you want to use. Yeah.
Actually, when I wrote WIMP papers, I also choose doublet plus all those odd numbers of multiplets. I'm surprised that you also choose the same set. Why didn't you choose the even ones?
Because I'm still working out the numbers for the year, to be honest.
Yeah. From my collider perspective, the even ones have more freedom in certain couplings. So I just choose them not to use those benchmarks. But for you, I don't think they matter that much.
I don't think they matter that much. You have to make choices to make sure that they're the even ones that there are more even candidates than odd ones. You have to choose the ones where like the lightest particle is neutral. So yeah, the even ones are to be put on display.
great. Let's thank Linda. And then we're gonna go for dinner, so if you wanna go, just.